Welcome to Hot Chips 33. Session 2. Academic Spinout Chips.
Hi, welcome to the next session at Hot Chips. I'll be your session chair. I'm Chris Drosanovich from UC Berkeley and Sci-Fi. This next session is on academic spin-out chips. Two exciting talks coming from academia out to startups and industry. So the first speaker is Karu Sankaralingam, and he's a professor at the University of Wisconsin-Madison. Based on a lot of the research he's done over the years in data flow machines, he founded this startup, Simple Machines, in 2017, and he'll be telling us about the technology that's been developed there in his talk. So please welcome Karu in his talk.
Good morning, everyone. My name is Karu. I am a professor at University of Wisconsin, and this work is done along with my colleagues Tony Nowadsky, who is a professor at UCLA, and my colleagues at Simple Machines. So I'm here to talk about our work, Mozart, and here it's really a philosophy on designing for software maturity and a new paradigm we're talking which is needed for chip architectures. So to begin this talk, let's look at where AI hardware and software stands today. First, the computational diversity in AI is increasing, starting from CNNs and ResNet about 5 years ago. We've had very dramatic evolution, including very new DL architectures like LSTM, transformers, and most recently graph neural networks and other things that are coming up every year. These are not just academic advances. These are production use cases in various different companies, which is shown by some of the annotations here. And many of these companies are using multiple of these things. So there's this big, diverse uses of various different DL networks or DL architectures. Second, coupled with this is the software user experience expectation is increasing. DL researchers and practitioners want essentially turnkey deployment. At some level, they don't care what your hardware is. They're like, I need this to work. I'm going to write the bare minimum amount of code. I want it all to work in a framework. Third, GPU software maturity, particularly NVIDIA with their deep learning software stack, is unrivaled in completeness. And that is allowing near complete dominance in AI industry deployment and among researchers. These two kind of go hand in hand. Because of this support or GPU support for model diversity, this is increasing GPU adoption. So GPUs are good at various different things and researchers just using them to build models using them, right? So this all sounds good. Is there a problem? First, GPU utilization is quite low. Oftentimes, you're running at like 10% of peak performance of a GPU. There are various things like batch size and so on, but largely they are underutilized in many scenarios. That's one problem and maybe an opportunity. Second, the software stack is very tied to what the hardware can do, using either auto-tune libraries or handwritten libraries. Because of this, ML systems are kind of just getting caught in the rut. And honestly, what's happening here is there's a little bit of the tail wagging the dog. Because only some styles of kernels achieve high performance on GPUs, ML practitioners just go and build models using those kernels that ends up in these ridiculously large models to get new capability rather than use better algorithms. And the opportunity here is these algorithms exist. They're hiding in plain sight. So one very influential work is the lottery hypothesis that shows simpler models with far fewer parameters have the same or superior learning ability. Second, there's an idea called depth-wise convolutions. This usually has 10 times fewer ops. But if you build a network using this, it actually trains slower or no faster than using conventional convolutions, if you will, which have 10 times larger ops because the hardware does not support these algorithms. So combining all of this with the diversity of AI models, how fast they are changing, and the increasing software user experience expectation, the opportunity and what needs to be done is new chip architectures must have software maturity to challenge GPU dominance to serve as an alternative. That's the way to go after this opportunity where GPU utilization is low and there are other things that can be done. So what do we mean by that? What is designing for software maturity? And then I'll get into details of our work. So the goal here is automated realization of the compiler, the entire software stack, using program synthesis techniques versus what I'm calling as human coding of high performance libraries or non-automated / imperative compilers. So the benefits of this is it allows what I'm calling as day zero software maturity. So when your chip is ready, your software is ready. Second, it avoids the pitfall of building software or refining your software after silicon arrives. Third, and this is underappreciated, we can overcome the problem of the fact that the software development cycle actually far exceeds the hardware development cycle. And if you kind of just go write manually tune libraries and so on, you just can't match the rate of change of applications. Fourth, from an architecture and hardware standpoint for our community, this allows co-design of the architecture to match the needs of the software because the software stack now exposes what the applications are doing. So I'll touch upon this briefly. There are definitely other IRs and compiler efforts, TVM, GLOW, and various other efforts. I don't have time to get into all of the technical details, but the gist of it is they don't get sufficiently down to the object code level or sufficiently up to the DL stack to serve as turnkey deployment for architecture development or new hardware you build. So that's the context where what we are exploring in this work and what we've been doing. And that gives us this paradigm called composable computing. This is an architecture paradigm that allows software maturity, including ideas of how the architecture is defined, and because of that, how we can define the hardware. So before I explain that, let me give you some context, and then we'll get into the mechanisms of the architecture and what's in the compiler, what's in the software. So here's a very high-level overview of conventional CPU execution of a deep learning application, right? So the source code has very, very rich semantic information, which is then broken up, and you end up destroying all that rich semantic information, and you have machine code in terms of primitive instructions. And then you spend a lot of resources on the hardware rediscovering the semantics of what was in the application, and you end up wasting a lot of resources for it. So with composable computing, we take a very different approach, and it roughly looks like this, and I'll break this up into the role of the architecture, role of the compiler, and how we're able to solve this challenge. So start with the source code that has rich semantic information. Then we have a compiler that looks at the source code and breaks it up into 4 coarse-grained behaviors we have found that can be used to build software super fast and an architecture that's efficient. So we need to achieve both. So that's the role of the behavior decomposition compiler. And the machine code essentially is not individual instructions, but it's an expression of these behaviors. I've been very abstract about these behaviors. What are they? These are intuitive. So there are really 4 behaviors that we've observed through the research we've done and the implementation we've built. One is data gather. Other is synchronize, as in communication between things. Third is compute. And finally, control, which coordinates all of this. And what's shown here is a tile level floor plan of the architecture we built. And the thing to note here is we're able to get this flexibility, software maturity, and the implementation lends itself to efficiency, as in hardware efficiency. Most of the transistors are devoted to compute, very little to overhead like control, synchronization, even data gather. So in the rest of this talk, I'll get into the details of the architecture, kind of bottom up, and then delve into the compiler role and how we tie this all up into the software stack. So here's the architecture overview and what this is built out of. So the color coding here is in terms of the 4 behaviors, and we'll walk through this organization here, right? So to get control, the architecture simply uses some simple microcontroller class cores. The job is to really sequence things, and instead of making them fixed state machines, having a simple programmable core allows you to get programmability and software flexibility, software maturity. Second are the 2 kind of most useful behaviors, if you will. One is compute, which is shown in blue, and the other is data gather, which is shown in gray. So to implement the compute behavior, we've developed a CGRA with a very novel data flow execution model where things are completely static, allowing a very efficient execution and allowing a compiler to map things super fast. But inputs are in terms of data streams, and these data streams are decoupled from the CGRA itself, allowing these data streams to either reside in a scratchpad memory or in a full hardware managed level 2 cache. And this is important because as model sizes grow and multiple models execute and so on, it's better to have that dynamism support and an architecture that supports that dynamism. And the underlying hardware is essentially, you can think of it as primitive functional units with a super efficient network that connects these functional units to each other. The job of the compiler is to create mappings. When we get to the compiler portion of the talk, we'll talk about how we tie both of those together. Finally, this is one tile. Multiple of these are necessary to run a large application, simply because there may be pipeline parallelism. Your application itself may be large, and you want to have modularity to be able to scale this architecture. And that's provided by an on-chip network that connects multiple of these together. So the high-level abstractions of this are, we have a graph. That's what the programmer sees, or the low-level programmer sees. There are 64 instructions in the graph, and then we have data gather, which is expressed in terms of these streams. And this architecture and this implementations allows 6 input streams. You can kind of think of this like as architectural variables, but a stream is a much more powerful concept of 6 is more than enough. You kind of think of it as how many tensors do I typically see going into a DL application layer, right? And we have 3 outputs. And the streams themselves have an address, they have a stride, they then specify ports that they target and so on. So that's the architectural abstraction that we built. That's at the heart of this composable computing paradigm. So the full SoC comprises of 64 such tiles. They are broken up into a hierarchy of groups of 16, and a group of 16 has a ring network that allows high-speed communication. And the architecture is implemented with an interface to HBM memory that gives us high bandwidth and very large capacity to run large models and multiple models simultaneously. The organization is very modular. It's multiple tiles connected together, and that's pretty much it. In addition, for the implementation, we have things like JTAG, SPI, SMBus, I2C, and so on. But those are all relatively straightforward and don't include a lot of additional glue logic. So that's the high-level organization. And the next thing I want to talk about is how do we expose this to programmers? How do we get high performance out of this and tie that all down to the compiler as well? So here's the kind of the performance view of it. So the way to look at this is bottom up. The tile shows up as a 64 functional unit array, It essentially has two modes. In non-SIMD mode, it can be executing every cycle 64 different operations. Or each function unit also has a SIMD mode. In that case, you can think of it as running 512 different operations. So inputs come in, they can come in from a cache, or they can be constants, or they come in from the scratch pad, and they are the ones that inject values into this array. And then the job of the core, which is doing this control behavior, is to just coordinate all of this. And in terms of synchronization and data gather, there's another core which does things like prefetch, managing things across chip, and dealing with other things that could be like managing a layer that you might spread across the different tiles, or handling things like pipeline parallelism, where multiple different layers are executing simultaneously, and you need to coordinate the flow of values. So this is where the three pieces come together: efficiency and flexibility, and making this software friendly or compiler friendly. We don't have fixed state machines or explicitly designed things that say one mode versus another. It's a programmable core that allows us to flexibly do one or the other. So the implementation is a chip we built called Mozart, which is implemented at 16 nanometer FFC with a 1 gigahertz operating frequency, die size about 400 millimeters squared. And as I said, this has 2 HBM channels, providing a total bandwidth of 512 gigabytes per second. So this is the production card is a 75 watt card, PCIe card, and for this implementation, Gen 3 X16 was sufficient. We did not need much higher PCIe bandwidth to implement the full system. So I'll touch upon some results, and then we'll get into the software stack and the compiler. So here's the full performance. We're comparing here to a NVIDIA A100, which obviously is much higher power consumption. Offline, I can talk about how these results look compared to an A10 or A30. We've also shown some projection for a 7 nanometer implementation. And roughly, the Mozart implementation at 16 nanometers is about 6x better sometimes. Sometimes we're only about 20% better. And DLRM is a pretty unique thing where there are these very, very large embedding tables, allows various levels of system optimizations, which we were not able to do on this implementation. And that's why we're actually worse than an A100, right? So the point here is very substantial application completeness and pretty competitive performance while being a technology node behind compared to the NVIDIA A100. And the rightmost column shows projections we've done on what a 7 nanometer implementation of this architecture could achieve. So now I'll dive into the software stack of this and get into the compiler, which is really ties into the software maturity piece, right? So this is a picture most of you have probably seen. There's the model, there's the parser, there's a compiler, and the underlying architecture, right? And we'll dig into how we're different, what our piece of software maturity is, right? So the high-level attributes are you get programmability and algorithm dependence, and the software is quite flexible, providing a C, C++ front end or Python SDK, or just get embedded into the DL stack. So how are we able to achieve software maturity? And a key to this is the role of the compiler and how we automate the creation of the software stack. So the way this is done, this is our compiler flow, and I'll walk through the pieces of this. So we start with a compiler that takes these behaviors, and as I said, one of the behaviors is the CGRA, the other is the stream engines, and that goes into the scheduler that's shown here. The job of the scheduler is to create these mappings onto the hardware of what goes where. It then creates the object file that gets embedded as part of our full software stack into A.out and the x86 binary and so on. This sits underneath the DL parser and all of that, which I'll come to in a moment. So that's the full software stack, and that's the compiler flow. So the most impactful piece of this is the compiler itself is at some level auto-generated, in the sense that we don't write reams and reams of code to create the compiler. The compiler uses integer linear programming, and the CGRA scheduler itself is only about 200, 300 lines of code, where the expression of the architecture is an input, and it is declaratively saying what should be done, what functional unit goes where, and as a result, we're able to create this compiler in terms of just its implementation very fast, and it also runs very fast. So that's, we'll talk about performance in a second. So to concretize this a little bit, here's an example of what actually happens, right? So on the left-hand side is a IR that shows individual operations of like addition, and here we call it a quantized top, which is a version of a Mac. And on the right-hand side is a mapping that's created, including the streams that come in and how these nodes send values to each other as this data flow engine executes. This is a mapping that's auto-generated by the compiler, and its job is to assign nodes, assign also communication paths such that they're all completely conflict-free. This gives us an execution model that looks like an ASIC, right? Things go exactly from one place to another without going and sitting in a register file and so on and so forth. So that's the low-level job of this compiler, and this ties back to all of the software stack to give us this software maturity. So tie this all together, we've been able to do more of all of the conventional things like graph optimization and quantization and mapping of tensors to memory and so on. Attach it to this essentially auto-generated compiler flow that produces object code through program synthesis, and a lightweight runtime where we've been focusing on inference. And this shows coverage across a broad class of applications where we can take existing TensorFlow pre-trained models, push it through this program synthesis-based flow, create a bunch of operations, do the quantization, and run it on the end hardware. And we talked about performance previously. Here's kind of a even more important or impressive version of this performance is the compile times of this entire flow. So this is not like hardware synthesis or HLS flow where you're taking hours or days to create mappings. This runs like what a software developer will want to see. It runs in a few seconds. So you can see the compile times range from about 8 seconds for ResNet, where you take a pre-trained model, do the validation of, run validation sets for quantization and so on, then create this final mapping. So that's really the end-to-end flow of this architecture, which exposes behaviors called composable computing. And then that allows us to build a compiler which has these primitives. And the compiler itself uses program synthesis to be built fast. And the architecture primitives allow you to have compilation times that are slow, and the execution of the hardware is fast. And the instantiation of the architecture makes it efficient. So to wrap up, I believe day zero software maturity is necessary for all future chips. So with the end of Moore's law and Attad scaling, architecture definition is a key challenge. And this definition must allow day zero software maturity. By that, what I mean is you need to be able to bootstrap your software for the architecture before defining it, or at least while defining it. Now, of course, the architecture itself must meet some figure of merit, right? Higher performance efficiency, or other things. In our experience, it's been validated that this effort and how we think about this problem, the chip implementation itself of a defined architecture is quite deterministic, right? There's a very, very well-defined flow, well-understood flow. There's about 8 months of exposure where you're doing the final physical design, where there's the manufacture and the bring up, where kind of nothing much can change. But outside of that, this pretty well-defined flow. And to conclude, program synthesis and this kind of auto generation of the software stack is necessary, I believe, for all future chips. And what we have done with the Mozart implementation and the composable computing paradigm is one compelling path forward, where the primitives of the architecture are very software and compiler friendly. And that allows you to get this day zero software maturity, and the architecture is efficient, allowing you to make a big difference in the field. So thanks for listening. I'm happy to take any more questions and dig into some of the more technical details or other topics that people are interested to inquire about.
Great. Thank you, Karu, for the great talk. Now we have a little bit of time for Q&A. So some of the questions that came up, one of them was related to how the compiler compares to NVIDIA's PTX in terms of what are the levels of representation inside the compiler. So the output of the behavior decomposition compiler, is that similar to NVIDIA's PTX or something else?
Yeah, that's a great question, and I'm kind of what's the word? Honored that someone would put us in the same league as PTX. But the gist of it is an intermediate representation in the sense that we are able to abstract away all of the details from the microarchitecture, but expose enough. At the same time, the thing that's different from PTX is we are lowering from high-level DL stacks down to this intermediate representation without kind of the breakup of cuDNN and other stuff that's there in the NVIDIA world. But the goal exactly is kind of like what's in PTX, right? You want a super productive and expressive layer that can get hardware efficiency and also be effective enough for a compiler to generate code too. I'm not sure if that was detailed enough, but we can get into more of that offline in Slack.
Okay, great. Yeah, I forgot to mention that was from Umar Darbaz at NVIDIA, that question.
Okay.
Okay, yeah, so next question actually is related to the company, I guess, and the product. So Charles Deliso from DSide Advisors is wondering about what is the product? Is it the IP, the compiler, the chips? This is actually partly my question too. So what is the product?
Yeah. So I mean, it's kind of like all companies. There's freedom to figure out. There's also necessity to be focused. So we built a piece of silicon. The default is to have it as a PCIe card. As you've probably gathered from the technology, there are various ways we could disaggregate it and explore different revenue opportunities. So that's how I would address it. I'm happy to talk more and then see how else we could take this forward.
Okay, great. Another question. This is from Anirban Ghosh from NVIDIA. So what are the runtime parameters on the A100? So they're basically asking you about the comparison you made with the A100, I guess.
Yeah,
a few other questions are in that space as well. You can say a little bit more about the comparison.
Yeah. That's a good question, and I want to be clear in what we did. So we did our own internal experiments, like probably many other companies, on running on V100, running on T4, and all the time you have to do a lot of tuning to get the best performance. So what we reported there are data we could gather whenever possible from numbers that NVIDIA has itself reported. So we believe those are kind of, in our view, best case numbers that NVIDIA has reported and obtained out of systems they've got. In a couple of cases, we didn't get the batch size comparison exactly that we wanted. So we did some scaling based on our internal modeling on how we think performance drops off when you reduce the batch size. So that's how those numbers are obtained.
Okay, great. Maybe the last question. This is from Elliot Rosen of AMD. And I think it's a question about the day zero software maturity model. So you apply it here to a certain kind of CGRA tile, but how does it apply to other styles of machine? Is it directly applicable, or is it something people are already doing for other template style machines?
Yeah, so I think I'm not sure I fully got the question. I think the question was, does this day zero software maturity apply for all architectures? Is it just for data flow and CGRAs? Yeah, I agree. Our view is This is for all chips we build. And the point here was we felt that with the small team we had, and also how I see as the complexity in building a compiler and software engineering, there is a role for what the architecture can do that makes that effort more tractable, especially when the applications are changing so fast. So that's why I think this is a dual effort with just not one or the other.
Okay, great. Thanks for a great talk and for the Q&A, Karu. I'm sure you'll be answering questions in Slack. So let's thank Karu in the Slack by uploading in the Slack. Great, so it's now time to move on to the next talk in the session. This is another startup that's spun out of academia. The presenter for this talk is Todd Austin. Todd is well known in the computer architecture community. He's a professor at the University of Michigan. He worked for a while at Intel Research Labs. He's also infamous for helping develop the simple scalar tool set that's widely used. He started a new startup, Attad Labs, which is working on security. And so his talk today is going to be telling us about Morpheus 2, which is a RISC-V based security extension for protecting vulnerable software and hardware. So please take it away, Todd.
Hi, I'm Todd Austin from University of Michigan and also Attad Labs, which is a startup that is commercializing a derivative of the Morpheus technology that I'm going to talk about today. I'm really grateful for this opportunity to present to you Morpheus 2, which is a second generation secure RISC-V CPU designed to protect vulnerable hardware and software from security attacks. And this is joint work with my colleagues at University of Michigan and University of Texas. So let's take a look at the state of today's security defenses. And as you can see from my slide, they're not good. We've got to worry all the time about data breaches and other kinds of software hacking. Perhaps one of the most notable incidents of this in recent past was the Equifax data breach in 2017, where one half of all American financial credentials was stolen. That includes social security number, address, name. But it's not just software and software penetrations and hacking that we need to worry about. We also have to worry about the people that make our software and use our software. Famously, the Cambridge Analytica abused the interfaces at Facebook to steal information about Facebook users. So we have to trust software. We have to trust the people who make our software, but I think often they're letting us down. Systems are not that secure. And there's really two main reasons in my mind why systems are not secure. The first being software, not just buggy software, but just any software. Because in my mind, all software is hackable. It's not hackable yet. It will be eventually when new vulnerabilities are invented and explored. And even if you could find and fix all the vulnerabilities, which is really, really tough, the software comes to you so quickly that you won't be able to keep up with that. This graph right here shows you the amount of lines of code running when a commercial airline goes wheels up off the ground. The blue line being for Boeing and the red line being for Airbus. And today, there's 50, 60 million lines of code running on these systems, and it's growing all the time. How do you make sure that's all secure? It seems impossible to me. The second problem, even if we could make sure our software had no vulnerabilities in it, the second problem we have to deal with is side channels. The systems we create leak tons of information in the characteristics of how they operate. So for example, how the program executes its control, or how memory is accessed, or how the timing of individual operations are occurring, or how caches are caching or not caching or conflicting with data, or how we speculate, not speculate. This all leaks information that attackers can use to pull secrets out of our systems. If we can solve these two problems, just untrust software and eliminate side channels, we can build much more durable security defenses. So how well are we doing at this? Well, we're pretty good on some fronts. We're actually pretty good at finding and fixing vulnerabilities. And we've got great tools like Valgrind and Coverity to help us do this. The challenge is, though, we don't find them all, right? We don't have anything that can reach closure on vulnerabilities. It's just not possible. So the attackers just have to find one vulnerability, and they're in. Now, when it comes to vulnerabilities, we understand very well system designers and hardware designers can introduce mechanisms that can basically shut down that vulnerability. great example is ARM's trust zone to stop memory attacks, and Intel's control enforcement to stop control flow attacks. These are very powerful mechanisms, but they specifically address a well-known attack scenario. Where we really fall short is on identifying and stopping emergent attacks. What's an emergent attack? That's an attack you didn't know about because it wasn't invented when you built your system. Now, does it seem unfair to ask designers to stop attacks that are invented in the future? Maybe, but they have to if they want to be able to build secure, durable systems. Just when I made this talk, there were 4 vulnerabilities that affected millions and millions and millions of systems that same week. So we have to. It may sound unreasonable, but you have to be able to stop attacks invented in the future. Can hardware security defenses be built to be more durable? I think the Morpheus project really points to the answer of yes. And I want to talk about how Morpheus 2 specifically works and what are the defenses it throws up against a very, important class of attacks called remote code execution. So let's take a look at Morpheus in more detail. First of all, Morpheus's approach to security is very unique. Whenever I describe it to people, it takes a while to sink in because the whole world today is really focused on vulnerabilities. How do we find and fix vulnerabilities? The challenge is endless because there's so many of them. There's new code coming all the time, and we don't have the machinery to find all the vulnerabilities. And we certainly can't find the vulnerabilities that are invented in the future, right? So we end up really not doing too well at that. So then the system ends up basically being vulnerable to attackers all the time. Yeah, you're always vulnerable. But in order for attackers to make an exploit, look at this equation here. It's a qualitative equation. Attackers need a vulnerability to get in. But once they get in, they need to manipulate the state of the machine to move around the security defenses. And that manipulation of the internal state of the machine is what's called, that combined with the vulnerability is what's called an exploit. Okay, I got your social security number. Okay, I manipulated the amount of money in my ATM account. That's the combination of the vulnerability and the manipulation of the the underlying assets of the program. And so what Morpheus does is it ignores vulnerabilities, completely ignores them. And it focuses 100% on implementation assets. And what it does is it does encryption and churn on those assets. So let's talk about just generally how does Morpheus work. Morpheus, it has these attack detectors that try to find monkey business, stuff that's going on that seems like it's not normal for a program. Now, it's not going to kill your program if you do this, but it's going to engage encryption and churn when that happens. So that's going to break a security attack. And the way it protects the system is it randomizes implementation assets. So things like code representation. The address space of code is randomized. The code pointer representation is randomized. Function pointer representation, return pointer representation. It can even randomize data pointers and microarchitecture mappings and data layout. It can randomize all these things. And if it does all that, it's got 504 bits of true random entropy that injects into the system so that the state of these things is unique in time and space. And so that's a huge amount of uncertainty to throw into the face of an attacker. They've got to reverse engineer all this stuff. Now, in the particular design that I'm talking about today, Morpheus 2, we randomize code representation, code layout, code pointer representation, function pointer representation, and return pointer representation. We'll see how that's done in a few slides, and we'll see how really efficient you can do that and how it really throws huge barriers up against some very important attacks. But before we go off on a little bit further, I want to just show you this video that was made for a few years ago for the Morpheus 1, but it's still relevant today. And it shows you how Morpheus tries to stop these attacks. This was made by these students who were the designers of the first Morpheus architecture. Let's take a look.
In a world where software vulnerabilities are rampant and unsafe languages like C are exceedingly common, attackers are gaining more power by the second. To synthesize an exploit, attackers need access to an asset, such as pointer values. Defenses randomize these values to make it harder for attackers. However, hackers have found help around these measures. there's hope. Because there's Morpheus. To stop attackers from de-randomizing assets, Morpheus changes it from under them in a process called churn. Morpheus is a secure architecture targeted at stopping advanced control flow attacks, such as ROP. We leverage hardware in RISC-V to provide 2 layers of defenses, displacing memory into a superimposed address space, and encrypting code and pointers. These defenses, combined with churn, significantly hinder exploits. With hardware support, Morpheus can churn sensitive assets every 50 milliseconds with less than 1% slowdowns. With information changing so quickly, attackers are left with a system that is extremely difficult to penetrate and must resort to advanced probing. Because of churn, this challenge becomes a race against a short clock, a race that is nearly impossible to win.
So the goal really is to create a significant amount of uncertainty in the system, so much that an attacker really can't solve that problem. I like to call Morpheus, it's really a puzzle that computes. And the puzzle part of it is the implementation assets. They're really difficult to discern in a reasonable amount of time. So let's take a look at that, how encryption and churn really protect those assets. So Morpheus uses those attack detectors to really discern normal code from malicious code. And when it sees malicious code, it engages its defenses. Or at some random interval, small interval, it engages its defenses. And specifically what it looks for is what we call undefined semantics. What is an undefined semantic? It is something that is part of the implementation of the system and is not defined in a way that is told to programmers. So, microarchitecture, undefined semantics and instructions, the underlying compiler implementation and the ABI and all this other stuff. These are things that are necessary for a working machine, but in no way is a normal program dependent on them. Now, normal programs don't care about undefined semantics, but attackers utilize undefined semantics. That is how they get their work done. If you study broad ranges of attacks, it is the undefined semantics and their utilization, their understanding, which allows you to step across security defenses. And so what we do is we encrypt and we randomize and we churn undefined semantics. So take a look at this. This is, on the first day of security class, you see this program. This is a buffer overflow attack where this function main calls vulnerable. Vulnerable has a small buffer, too small. It overwrites string 1, which is passed in, which overwrites the return address of vulnerable with this pointer that's embedded in the string. And so instead of vulnerable returning to main, vulnerable jumps to target. Boom, I own your machine. And you can see there's 3 undefined semantics here. Going past the end of an array, undefined in C, undefined in C++. Putting a pointer into a string, completely undefined. That's pointer forgery. That's not defined. Pointer is defined by taking the address of an object. Even the representation of a pointer is not defined. And then finally, the manipulation of a return address. The return address isn't even defined. There's no return address in the definition of a language. It just functions return. We don't know how they return. So the manipulation of a return address, other than by the instructions created by the compiler, is absolutely an undefined semantic. So to stop these attacks, even unknown attacks, Morpheus uses encryption to randomize all of the undefined semantics. And it re-randomizes these assets with a process called churn by rekeying the encrypto that is used to define the representation of pointers and the representation of code. By doing this, you end up breaking security attacks because the attacker goes, where is the return address? The attacker goes, what is passes the end of this array? The attacker goes, how do I represent this pointer in a string? They don't know. They have to discover that information. And they have to discover that information before churn engages. Otherwise, it's completely a different solution. So churn really limits the rate that the amount of time they have to do this discovery process. And we can even learn those different aspects of how an attack occurs, and we can reorder how we engage these defenses to be even more efficient at stopping attacks. So let's see how Morpheus can stop an emergent attack, an attack it's never seen before, ever, invented after the system was deployed. In a typical attack scenario, you might probe for a little bit of information, a couple milliseconds worth, synthesize an attack the system, success. if Morpheus were to engage encryption, 504 bits across all kinds of different undefined implementation assets, the system would still be totally hackable. Trust me, because attackers are great at reverse engineering what they don't know by just manipulating and exercising the system. But it would take them hours, a long, long, long time to figure out how to get through those 504 bits of key entropy, because they'd have to use side channeling. How do things interact in the caches? How do things interact in the BTP, etc.? They'll get in, no problem, but it'll take them a long time. When you engage churn, when you rekey the randomization defenses using encryption, then essentially you just create this endless loop where they try to discover the information, they don't learn it in time, they lose any traction they've made. And that continues and continues and continues. And if you learn how an attack works and you engage defenses more effectively, you can even reduce that amount of time. So it's an incredibly powerful defense that leverages uncertainty to stop attackers. So let's take a look at how you can inject this encryption and churn for code and code pointers into a RISC-V Rocket Core pipeline, and see this working in action. Then we'll see our analysis of it. So again, we're going to encrypt code. Where are we going to encrypt code? Everywhere, everywhere. So it can't be stolen. So caches everywhere, all the way up into the pipeline. Where are we going to encrypt code pointers? Everywhere, in the memory system, in the DRAM, in the caches, in the registers. Now, this forces us to add instructions. That's an instruction set extension that we made for RISC-V, which manipulates encrypted pointers. So it takes an encrypted pointer, it does an op on it, gives you an encrypted result. It can compare to encrypted pointers. It can dereference an encrypted pointer. It can jump to it, for example. And these are just instruction enhancements. Now, one of the things we did that was really successful on Morpheus is we don't have to tag the system. Normally, when you do a secure system, you'll have some encrypted pointers here and some unencrypted pointers there. These are special, protected pointers. These are not. And we tag everything, and the tags propagate through the memory system and the registers, and there's tag calculus, and oh my gosh, it's horrible. You basically puke out complexity into your entire design. What we did is we just said, every pointer is encrypted under this unknown key that was generated by a TRNG. No tagging required. Really, really simplifies the design. You got to take crypto into your pipeline, though, which is a potential risk. And then these ops are all leaky. Like when you compare two pointers, that gives you a decrypted result. You can use that to side channel your way in. So we want to engage churn on a regular basis in this system. Here's the RISC-V Rocket Core microarchitecture enhanced to do our two special things. Encrypted code. Encrypted code comes encrypted out of the L1 data cache right into the fetch stage, and then it gets decrypted on the back end of the fetch stage. So there's only one stage you have a decrypted instruction inside decode, and then it pukes out all the control signals, and that's the end of your instruction. So that is a small window of opportunity to steal that instruction. And then when you do an indirect jump in the form of a return or a call through a pointer or a function jump through a pointer, we have to decrypt the code pointer. There's an extra stage added after that pointer is identified before it goes into the PC, which is this second green arrow. And again, even in the register file, even in the caches, all the code pointers are encrypted. There's nowhere to steal them except on those wires right here. You can steal them on those wires. You can figure out how to read those wires. I don't know how to do that. So it's a real powerful mechanism. These two defenses combined are really effective at stopping what's called remote code execution. That's where someone's trying to inject their code into your system, because they have to manipulate your code, understand your code, and manipulate your code pointers. This happens to be one of the highest value attacks that exists today. If you were familiar with the Microsoft Exchange server attack, which Microsoft spent the whole last summer trying to fix again and again and again, that was a RCE attack, a remote code execution attack. So they're very high value attacks. And as you can see, there's just a wide range of attack classes you could stop here with just these two simple mechanisms. It's really an effective set of mechanisms. So let's take a look at our performance, area, power, security analysis for Morpheus 2. We deployed Morpheus 2 on the RISC-V Rocket Core. We only added 369 lines of chisel code where we love chisel. It's a very effective framework. Takes a while to learn, but what you do, it's kind of an expert-friendly environment. 369 lines of code. That includes our crypto engine as well, too. So, and we deployed as part of the DARPA SITH program, we deployed into Xilinx UltraScale Plus FPGAs. You can see one here underneath that fan. Our crypto engine was a 12-round Simon cipher. That's not full-strength Simon. It's what we could fit in one cycle of the RISC-V rocket core. But that is semi-strong crypto. That is not like XORing with a key. That is, you got to do cryptanalysis to reverse engineer that within the time it takes to churn. And the overheads are low, right? We got a little bit extra delay in the front end, a little bit of delay on indirect jumps, less than 1% performance hit, less than 0.2% power overhead. We don't even increase the size of pointers, and about 1.3% area overhead for our crypto engines. And when you run network apps on this thing, you can't tell. If I'm asking you, is this the protected, the unprotected means you can't even tell. It's really got a low footprint overall, and a really high security defense. So as part of the DARPA SITH program, at the end of the program, one of the gates to getting through the program is you had to go into what's called the FET challenge. And the FET challenge was a commercial red teaming of your target. So it was done with a company called Synac in Redwood, California, which has, these sort of world-renowned security researchers they work with, and they come and attack your system. We were deployed into Amazon AWS F1 FPGAs. We had 535 attackers sign up for our target. They worked for 3 months solid. And for sizable bounties, we weren't fully knowledgeable of all that aspect of the design, but we were told that the bounties were at least $50,000. And we put up a challenge app, which was a website running a REST API that gave access to a mock medical COVID-19 database inspired by 2020. And that was running over a database and then an operating system. And we didn't have virtual memory. The entire stack was hackable anywhere. We supplied it to the attackers with known vulnerabilities in the system because SITH was really hardware to protect vulnerable software. So they were aware of vulnerabilities, in particular in the SQLite database stack. And our target was the second most engaged target out of 7 that went into that program. Had the program gone on a little bit more, they were kind of heaping extra bonuses on us. So had it gone on a little bit longer, we probably would have been the first most attacked target. And we had zero penetrations. I talked to a few months ago, I talked to a grizzled old pen tester who works in the commercial sector, and he said he'd never heard of a multi-month pen testing effort not reveal at least one vulnerability, not a single vulnerability in Morpheus. So there's something here. What is that something? I shall ask now. When we went into the effort, I was fairly certain we would do well. I didn't know we would be zero vulnerabilities. I mean, personally, I think Morpheus is hackable, right? The next generation Morpheus, maybe not. We'll see. That's what we're working on right now. But Morpheus it's got side channels in it still. But I hired this incredibly talented undergrad, Shibo Chen, to start hacking on the system a year before anybody else had access to it. And we learned a lot of stuff from it. It is hard to forge pointers. It is hard to forge code. It is hard to understand the address space in the system. And you can probe to learn that information, but that information dissolves the moment the system churns. So it is really difficult. And that is really across any attack that utilizes code and code pointers and the address space of code. So, I mean, that's a lot of attacks. That is a wide swath of attacks. So, if you're going to attack this machine, it's got to be basically a bespoke and lightning fast attack. It's basically probably going to be a stochastic style attack. It'll be hard. So, going forward, I really want to sort of lean into this kind of uncertain design, utilizing cryptography and doing better on side channel elimination than Morpheus. So, and I really see that the way to deal with uncertainty is really to, lean into cryptography. That's the most durable defense that exists on the planet. And it's a great way to create uncertainty in the system. And then the way we solve side channels is we really have to lean into physical isolation. We've got to bring our critical computation off the main core, and we need to put it into something that is as silent as a mouse for side channels. If we can do that, we can build something really amazing. And that's what we're building at Edge of the Labs. That's the start I'm at. We're building what's called the Ozone SPU, which stands for Secret Processing Unit. It's a coprocessor that performs computation of the form we call secret computation. Secret computation is physically isolated from all the rest of the system by strong cryptography. You only see random crypto come in and out of it, and physical isolation to eliminate the side channels. And we're deploying this in the FPGAs in the Microsoft Azure and the Amazon AWS clouds. And this, in our estimation, will be significantly more secure than the Morpheus 2 target. So we're super excited to make this available for people to try out. So thank you so much. If you want to learn more about that, please contact me. Just thank you so much for this opportunity to present today. I'd be glad to answer any questions. I'll stick around as long as I can to do that. Thank you so much. Take care. And there's my email address if you'd like to contact me.
Okay, thanks for the great talk, Todd. Very interesting stuff going on there, very exciting. We had a few questions show up in the Slack channel. So one in particular had a lot of upvotes was, this is from Gabriel Southern at Qualcomm, one of the HotChips people. What's the impact on the programmer's debugging experience on a system with so much randomized state? And I think I would add to that both native debuggers, but also hardware debuggers attached to the core.
Fantastic. Okay, so for debugging, there's really two interesting aspects about debugging. You basically need to share the key with the debugger so that you can actually understand the value of the protected state in the program. So there's a way to run with a fixed key, and the debugger has the fixed key. And then when you go into production, you run with the TRNG key. The second interesting thing about debugging is Morpheus breaks buggy programs, because if you have programs which are buggy because they are misinterpreting pointer and code values as not being pointer and code values, the churning of those values tends to break those programs more readily. They may have, those bugs may lie dormant in those programs before, but when you turn on Morpheus. So we actually found, you can find a few bugs in software with this technology as well.
Okay, so another question is on similar lines. Some of the hacks, people put sleeper code in there, awaiting activation. Can you cope with that kind of code where there's Trojan horses code already embedded in the application?
Not Morpheus. So Morpheus can't stop an inside job. Anything that's inside the program runs inside of the encryption shell. And so it can express any pointer it wants. It can manipulate any pointer it wants. So if there's malicious code inside of there, then that it won't be able to stop that. And in fact, Morpheus's strength is really stopping people from outside the process shell trying to get in to manipulate the state of the program. So the classic version of this being the runtime code execution attack. That said, at the startup, we're sort of keenly aware of these particular kinds of inside job malicious code attacks, and that's something that the next generation of Morpheus will be concerned about.
Okay, I think unfortunately we've run out of time for Q&A. I'm sure Todd will be around to answer more questions in the Slack channel.
I'll stick in the Slack and make sure they all get answered. Thank you so much.
Okay, great. Thank you, Todd. Okay, so that's the end of the academic spin-out session.